Welcome to the deep dive. Today we're preparing to zoom out, way out, exploring the universe based on this really fascinating set of sources you shared.
That's right. We're covering everything from, our local cosmic neighborhood right out to the edges of what we can actually observe.
And it taps into that ancient human fascination, doesn't it? Looking up, wondering.
Absolutely. For millennia, we've gazed at the night sky. We've gone from myths about gods and spirits in the stars to the incredible scientific understanding we have now.
Exactly. So our mission here on this deep dive is really to pull out the most compelling, the most important insights about the universe from these materials.
We want to give you a clearer, maybe more engaging picture of just how vast everything is.
Right. We'll navigate from our solar system, the sun, the planets, all the way out to galaxies, and this idea that the universe is expanding.
So the universe itself, our sources define it pretty simply. It's everything, all of space, all the matter, all the energy within it.
But what's striking is, even with all our science, its actual size, whether it even has boundaries,
Yeah.
that's still unknown.
It really is. It puts our own existence into perspective, doesn't it? Earth is just this tiny speck.
A tiny speck.
Okay.
Let's focus on those lights we see at night, the stars. Celestial bodies that, crucially, make their own light. They twinkle.
Uh-huh. And a common question is, where do they go during the day?
Right.
Well, they don't go anywhere. It's just that our sun, our star, is so overwhelmingly bright.
It just washes them out.
Exactly. It floods the sky with light, making the fainter, distant starlight invisible to us. But they're still up there.
Okay, so they're just outshone. Now, stars are different from planets, like our Earth.
Right. Planets have a steadier light because they're reflecting starlight, usually from their parent star.
And they follow paths, orbits around those stars.
And often, orbiting the planets themselves, you find satellites, moons.
Like our moon, Earth's natural satellite, held there by gravity.
It's quite amazing that just with the naked eye, on a really clear night, you can see maybe around 3,000 stars.
And then you think about what a telescope reveals. It's countless.
And the distances between them are just mind-boggling.
Which brings us closer to home, to our solar system.
Yes, our sources define that as, everything gravitationally bound to our sun. That includes the planets, their moons, asteroids, comets, meteors, the whole system.
And the name solar comes from sol, the Latin word for sun.
Precisely. The sun is the star at the center of it all. Estimated to be about, 4.5 billion years old?
It looks huge to us, but that's mostly because it's close, relatively speaking.
Exactly. There are stars out there far, far larger, but they're so distant they just look like pinpricks.
Which means we need different ways to measure these distances.
Which is where the light year comes in. Our sources introduce this concept.
Okay, a light year. Let's unpack that. It's the distance light travels in 1 year.
Correct. And light travels incredibly fast. So 1 light year works out to about 9.46 trillion kilometers. That's a 9 with 12 zeros after it.
Trillions of kilometers, just staggering.
And to give that some context, our own sun, which feels so close and essential, is about 150 million kilometers away.
Still a huge distance.
It is. Light itself takes about 8 minutes and 20 seconds to travel from the sun to us.
So the sunlight we feel right now actually left the sun over 8 minutes ago.
That's right. You're always experiencing the sun as it was a little bit in the past.
And compared to Earth, the sun is enormous, about 100 times our diameter.
And its mass, over 1 million times Earth's mass. It's just immense.
The temperatures, too, around 6,000 degrees Celsius on the surface.
Roughly, yes.
Man.
And inside, in the core, it gets up to about 15 million degrees Celsius. Just incredible heat.
And it's made mostly of hydrogen and helium.
Overwhelmingly, yes. It's basically a giant glowing ball of these gases, a natural nuclear furnace.
And that furnace provides all the heat and light for the solar system, making life possible here on Earth.
It's the engine. The energy generated in its core through nuclear fusion sustains everything.
The sources also break down the sun's structure into layers, though they mention the transitions aren't like sharp lines.
Right. It's more gradual. Outermost is the corona. Very low density, but surprisingly hot, around 6,000 degrees Celsius again, though some parts are much hotter.
Then below that, the chromosphere.
Thousands of kilometers thick, and even hotter on average than the corona, reaching maybe 28,000 degrees Celsius. It's still an active area of research why these outer layers are hotter than the surface.
Interesting. And then the photosphere.
That's the layer we typically see, the visible surface, relatively thin, maybe 550 kilometers thick.
And finally, the heart of it, the core.
Yes, the core. Temperatures hitting that 15 million degrees Celsius mark in the very center. That's where the magic happens, so to speak.
Where hydrogen fuses into helium.
Exactly. Nuclear fusion, releasing just tremendous amounts of energy. That's what's powered the sun for billions of years and will for billions more.
Okay, let's shift from the star to the planets. The ancient Greeks called them wanderers.
Right, because unlike the fixed stars, the planets appeared to move across the night sky over time.
And they don't make their own light, they just reflect sunlight.
Correct. And there's a basic relationship.
Mm.
The closer a planet is to the sun, the faster it has to orbit to stay in its path.
And among all the planets, Earth is unique. The only one we know that supports life.
For now, at least. And they travel in these large elliptical paths, orbits, not perfect circles.
Now, historically, many of us learned about 9 planets. Pluto was included.
Yes, but our understanding evolved. The International Astronomical Union, the IAU, set up new definitions. Now we talk about 8 classical planets and then dwarf planets.
Right. So what makes a planet classical? 3 things.
1, it has to orbit the sun. 2, it needs enough gravity to pull itself into a nearly round shape.
Okay.
And 3, it has to have cleared its neighborhood.
Cleared its neighborhood, like it's cleaned up its orbital path?
Sort of, yeah. It means it's the gravitationally dominant object in its orbit. There aren't other large bodies sharing its path, except maybe its own moons.
And that's the key for Pluto.
That's the main reason, yes. Its orbit is quite elongated and tilted, and it actually crosses Neptune's orbit. So it hasn't cleared its neighborhood.
So it got reclassified as a dwarf planet, along with others like Eris, Sirius.
Yes. Sirius is interesting because it's in the asteroid belt.
But whether classical or dwarf, they're all basically spherical, relatively cool compared to the sun.
And they rotate on their axes, giving us day and night. The sun rotates too, actually.
And the time for one spin is the period of rotation.
Right. So let's take a quick tour of the classical planets, starting closest to the sun, Mercury, Bood.
Smallest, second hottest. Sometimes it's called the morning or evening star.
That's right, because it's often visible near sunrise or sunset. But conditions are harsh, no real atmosphere, so huge temperature swings between day and night.
No life possible, no moons.
Then Venus, Shukra. Often the brightest thing in the night sky, besides the moon.
Why so bright?
Because of its incredibly thick, cloudy atmosphere, mostly carbon dioxide. It reflects sunlight really well.
But that same atmosphere makes it the hottest planet, right? Runaway greenhouse effect.
Exactly. Hotter even than Mercury. It's very similar in size to Earth, slightly less massive, also no moons, and definitely no life.
Okay, then planet number 3, Earth. Prithvi, home.
Our unique world. Liquid water, a protective atmosphere with nitrogen, oxygen, the conditions for life.
Its tilt gives us seasons, its rotation day and night, and its orbit defines our year 365.25 days.
And we have our one natural satellite, the moon.
That tilt and orbit combination. That's key for seasons, isn't it? How one hemisphere tilts towards the sun while the other tilts away.
Precisely, leading to summer in one hemisphere and winter in the other.
Moving outwards. Mars, Mangal, the red planet.
Yes, that reddish color comes from iron oxide, basically rust on its surface. Thin atmosphere, much thinner than Earth's, mostly carbon dioxide again.
But easier to see the surface because the atmosphere is thin.
Relatively, yes. And there's been so much interest in Mars. Signs of past water, speculation about life.
But no definite proof yet.
Not yet, but missions are constantly searching. Mars has 2 small moons, Phobos and Deimos.
Now we get to the giants. Jupiter. Brihaspati.
The king! Largest planet by far, 318 times Earth's mass.
And surprisingly bright, even though it's far out.
Yeah, it reflects sunlight well off its thick atmosphere, mostly hydrogen and helium, with those characteristic bands of clouds containing things like methane and ammonia crystals.
Visible to the naked eye. And it has a huge number of moons. How many?
The count keeps going up. Last I checked, it was over 90 confirmed moons.
Wow. Okay, next is Saturn, Shani. Second largest.
About 95 times Earth's mass, and famous, of course, for its stunning rings.
So those rings, visible with even a small telescope.
Oh, yes. They're made of countless icy particles, truly beautiful to see. Saturn's also visible without a telescope and has, well, also a very large number of moons, over 80 confirmed.
And it's the least dense planet. It would float in water, theoretically.
That's the classic analogy, yes. Less dense than water.
Further out still, Uranus.
Appears as a small blue-green disk telescopically, much larger than Earth, diameter about 4 times ours, Atmosphere of hydrogen, helium, and methane. The methane gives it that color.
And it rotates funny, doesn't it? On its side.
Almost exactly on its side, yeah. Its axis is tilted nearly 98 degrees relative to its orbit. Very strange science. It has 27 known moons,
And finally, Neptune.
about 17 times Earth's mass. Very distant, very cold. Not visible without a telescope. It has 14 known moons.
Okay, let's loop back to Pluto. Dwarf planet now.
Right, out in the Kuiper Belt, beyond Neptune. Extremely cold, dark, and small, maybe 0.2% of Earth's mass.
Definitely need a telescope. Takes almost 250 Earth years to go around the sun once.
And it has 5 known moons, including Charon, which is quite large relative to Pluto itself.
Okay, we've mentioned moons a lot. Natural satellites, they orbit planets, right?
Correct. Non-luminous bodies held in orbit by a planet's gravity. Our moon is the prime example for Earth.
And it shines because it reflects sunlight. We can see bright highlands, darker plains.
Right. The brighter areas are older, heavily cratered highlands. The darker areas, the Maria, are younger, smoother plains formed by ancient volcanic flows.
And humans have been there. Apollo 11, 1969. Armstrong and Aldrin.
A monumental achievement. They found a rocky, dusty desert, no water, no vegetation.
And hardly any atmosphere because its gravity is so weak.
Only about 1/6 of Earth's gravity, yeah. Not enough to hold on to a substantial atmosphere.
Which leads to those extreme temperatures. Boiling hot in sunlight, freezing cold in shadow.
Around 100 degrees Celsius daytime, down to maybe minus 170 Celsius at night. Not hospitable.
But visually, from Earth, the moon is fascinating because of its phases.
The changing shapes we see. Our sources explain it's just us seeing different amounts of the sunlit half as the moon orbits Earth.
Starting with the new moon invisible, basically.
Because the side facing us isn't lit by the sun, then a sliver appears, the crescent moon.
About a week later, half moon first quarter.
Then more than half the waxing gibbous, leading up to the full moon when the whole face we see is lit up.
After full moon, the light starts shrinking. Waning gibbous.
Then half moon again, third quarter, then a waning crescent, back to new moon.
And that cycle, full moon to full moon, is about 29 and a half days, the basis for a month.
Roughly, yes. Physically, the moon's about 3,500 kilometers in diameter, orbiting us at an average of 384,000 kilometers.
It orbits west to east, but looks like it moves east to west because Earth spins faster.
That's the apparent motion, yes. But the truly cool thing is synchronous rotation.
Meaning?
It rotates on its axis in almost exactly the same time it takes to orbit Earth.
So, we always see the same side.
We always see the same face, yes. The dark side isn't always dark, it just always faces away from Earth.
Okay, let's talk tides on Earth. The rise and fall of the sea.
Typically twice a day, yeah. Driven mainly by the moon's gravity.
How does that work? The moon pulls on the water?
It pulls on everything, but water responds most easily. So the water on the side facing the moon gets pulled into a bulge high tide.
Okay.
But interestingly, there's also a high tide on the opposite side of Earth.
Why there?
Because the solid Earth itself is being pulled towards the moon slightly more strongly than the water on the far side. So the water there kind of gets left behind, forming another bulge.
Ah, I see. And low tides happen in between those bulges.
Exactly. In the areas perpendicular to the moon's pull, it takes about 6 hours and change between high and low tide.
And these tides are useful. Power generation.
Yes, tidal power is a thing. They also help flesh out harbors and coastlines and allow large ships to enter shallower ports during high tide.
Okay, zooming out again. Galaxies. That faint band across the sky. The Milky Way.
That's our home galaxy, seen edge on from the inside. A galaxy itself is this enormous system of stars, gas, and dust, all bound together by gravity.
Billions of stars in just one galaxy.
Hundreds of billions, typically. And there are maybe hundreds of billions, possibly even trillions of galaxies in the observable universe. They're the basic building blocks.
And they come in different shapes. Spiral, elliptical.
Irregular, yes. And even starburst galaxies, which are forming stars at a really high rate.
Our Milky Way, or Akashganga, is a spiral galaxy.
That's right. If you saw it from above, it would look like a pinwheel with spiral arms coming out from a central bulge. Since we're inside one of those arms, we see it as that Milky Band. It's huge, about 100,000 light years across.
Now, within galaxies, people saw patterns in stars. Constellations.
Exactly. Ancient cultures connected the dots, saw shapes, animals, heroes, objects, and told stories. We now officially recognize 88 constellations covering the whole sky.
Like Orion the Hunter in winter, Ursa Major the Great Bear.
Scorpio the Scorpion in summer, yeah. Ursa Minor, the Little Bear, containing the North Star, Polaris.
And we see different ones at different times of year because Earth moves around the sun.
Our viewpoint changes, and because of Earth's movement, any given constellation appears to rise about 4 minutes earlier each night.
So, just to be clear, galaxy versus constellation.
Big difference. Galaxy. Billions of stars. Immense structure. Countless galaxies exist. Constellation. Just a perceived pattern of a few relatively nearby stars from our viewpoint, only 88 official ones.
Okay. And measuring distances.
Yeah.
Light years, we covered that. What about parsecs?
Another unit for even larger distances. 1 parsec is about 3.26 light years. Just different scales for the vastness of space.
Got it. What else is out there? Comets?
Luminous bodies, often in very long elliptical orbits around the sun, made of ice, dust, rock.
And they grow tails?
When they get close to the sun, yes. The sun's heat vaporizes the ice, creating gas and dust tails that get pushed away by sunlight and the solar wind. Far from the sun, no tail.
Like Halley's Comet, which comes back every 76 years or so.
A famous periodic one, yes, last seen in 1986.
Then there are meteors, shooting stars.
We call them that, but they're not stars. They're small bits of rock or metal, maybe debris from comets or asteroids.
That burn up in our atmosphere.
Exactly. Friction with the air makes them glow brightly as they streak across the sky. Most burn up completely.
But if one survives and hits the ground...
Then it's called a meteorite. Larger ones can make craters.
Okay. And asteroids.
These are like minor planets, mostly rocky bodies. They mainly orbit in the asteroid belt between Mars and Jupiter.
Thousands of them known? Millions, maybe?
Over 1 million have been cataloged, yes. Ceres is the largest, discovered in 1801, and it's also a dwarf planet now.
And the theory is they're leftover bits from a planet that didn't form or broke up.
That's a leading theory, yes. Possibly due to Jupiter's immense gravity disrupting things early on.
Fascinating. Okay, eclipses. Sun, Earth, Moon lining up.
That's the key. The sun shines, Earth and Moon reflect. When they align perfectly, shadows get cast.
So a lunar eclipse is when the moon goes into Earth's shadow.
Correct. Earth is between the sun and moon. If the moon goes fully into the darkest part of the shadow, the umbra, it's a total lunar eclipse. It's partial. Always happens during a full moon.
And a solar eclipse.
That's when the moon is between the sun and Earth, casting its shadow on Earth.
So from Earth, the moon blocks the sun.
For observers in the right spot, yes. If the moon completely covers the sun's disk, it's a total solar eclipse. You might even see the sun's corona, its outer atmosphere, briefly. This happens only during a new moon.
But crucial safety warning. Never look directly at a solar eclipse.
Absolutely never. It can cause permanent eye damage. Use certified eclipse glasses or project the image safely. Never binoculars or telescopes without proper filters.
Good advice. Now, shifting gears. Artificial satellites. Man-made objects orbiting Earth.
Right. Launched by rockets, needing a minimum speed about 8 kilometers to reach orbit.
And the higher the orbit, the slower they go and the longer they take.
Generally, yes. Inverse relationship between altitude and speed period.
Started with Sputnik I in 1957.
USSR, yes. Then the US with Explorer 1. India joined with Aryabhata in 1975.
And many since. INSAT series, IRS for remote sensing, the Mars orbiter mission.
MOM, yeah. A huge success for India. These satellites are now indispensable.
For TV, radio phones.
Telecommunications, weather forecasting, GPS navigation, remote sensing of Earth's resources, agriculture.
Studying space, locating minerals. The list goes on.
They're vital tools for modern life and science.
Finally, the really big picture. The expanding universe.
Based on observations by Edwin Hubble and others, galaxies aren't fixed, they're moving away from each other.
And the farther away they are, the faster they move away.
That's Hubble's law, yes. The inescapable conclusion. The whole universe is expanding.
Which leads to the Big Bang Theory.
The prevailing model for the universe's origin. It suggests everything, all matter, all energy, started in an incredibly hot, dense state.
How long ago?
About 13.8 billion years ago. This state then underwent a massive, rapid expansion, the Big Bang.
Flinging matter outwards, which eventually cooled and formed everything.
Over billions of years, yes. Gravity pulled matter together to form stars, galaxies, the large-scale structures we see. The cosmic microwave background radiation is strong evidence for this hot early phase.
Okay, so just to recap planet versus satellite differences again quickly.
Sure. Planets orbit the sun. Satellites orbit planets. Planets are generally bigger. We have 8 classical planets, many dwarf planets. Satellites are smaller, hundreds known orbiting planets in our system. Both rotate on their axis.
And the sources included that table with all the planetary data: distance, size, rotation, orbit time, moons.
Right, it gives you a really good snapshot of the diversity just within our own solar system, comparing Mercury to Jupiter, for instance.
So wrapping up this deep dive, based on all this incredible material,
Mm.
the scale is just overwhelming.
It really is. From our tiny planet to the edge of observability, the complexity and wonder are profound.
It really makes you think, doesn't it? What does an expanding universe really mean? Where do we fit in?
Good questions. And it prompts further reflection.
Yeah, like a final thought for you listening. Consider how far our understanding has come. From myths
Mm.
to complex physics,
Yeah.
what discoveries are still out there waiting.